Welcome to the 2021 Wilmington Spring Workshop. What I'm going to talk about now is a new, very extensive course that's, to me, well overdue. It's a Mesoscale Environment Analysis um, uh, CLC called MIA. It's a foundation for enhancing your severe convection IDSS. And down at the bottom, you'll see names. And Peter Wolf and Dr. Cohen on the right. Peter is the Sioux in Jacksonville, and Ariel Cohen is now the MIC in Pueblo. He was a Sioux at Miami and also Topeka earlier. And then other people, Chauncey Schultz, I think, in North Dakota, a bunch of other Sioux, Brian Haynes from Philadelphia, and so forth, had contributed to this course. And you'll see it's very, very extensive. And we will go to the next slide. So I'm going to put this. Everybody's hopefully their phones are on. Would you issue a tornado for this storm? Just from the pictures. Anybody?
I assume
Yes.
it's correct, but probably
David and
not.
I would.
Okay. Okay. Now, what happens if I told you, if you knew the winds were from the northeast and the capes were small, would you still issue a tornado warning? What about Stephen?
Yes.
Okay. What if you knew that there was surface frontal inversion aloft and a cold front to the south? Would you issue a tornado warning? The answer to that is no, you probably would not. So it's just looking at the radar. You need to use mesoscale analysis. I know I'm not saying it's never used in the office, but I know it's used pretty frequently, and it shows you how important using all your tools, just not radar, are important. They came back, and you'll see in their presentation, they said there's two approaches to severe operations. There's the recipe approach. You don't need any science. All is written for you, and it's just reactive. You respond one action with another. A new radar picture comes in, fine. I don't look at the satellite. I'm not looking at the surface obs. I'm not looking at the meso analysis from SPC. It's a safe approach. Guidelines requirements are there, and it's responsible for some of our errors. The science approach of severe storm operations, you're trying to predict and anticipating. You're proactive, you're predictive, you're just anticipating. You have to make decisions, often without supporting guidelines or requirements to back you up. Sometimes you'll be wrong. They showed that these are the current GIPR goals, and to be honest with you, what he was saying is they've become stagnant or even become a little worse over time. And to help going with the scientific approach, we probably can increase some of that better, because the radar is to a point where the physics is physics, and we're not going to be getting, radars with 50-meter dishes and things like that to get like a quarter degree beam width and more radars elsewhere around. So when utilizing the radar in the recipe approach, the radar tells what the actions are to take. That is a tornado for a moderate rotation signature. But the science approach, the radar confirms are just what you were expecting and predicting. Course environments can change easily across a state line or CWA. Example someone mentioned earlier about the marine layer. The differences, you probably can have a little more accuracy. Your lead time can be better, and it's about giving value added to what the radar has. And of course, when you anticipate it and get a little bit longer lead time, there's great job satisfaction. So that's kind of the unknown thing that helps everyone's personal ego. Why the science approach? He gave an analogy. This is from his thing Peter did. I just liked it a lot because it had to do with food. But let's say you're making cookies. The recipe calls for 1 tablespoon of baking soda. And when you discover you have no baking soda, what do? Well, the recipe approach, you would follow the recipe with what you have, and well, it usually wouldn't taste too good. Let's say it was cookies, chocolate chips. But the science approach, You go, well, what can I do? Well, you Google for baking soda substitute and you utilize baking powder. Hey, and the cookies are yummy. So the science approach will help you uh, with the warning operations and know what to anticipate. Just remember, a thunderstorm does not know its location. It doesn't know the time of year, if a warning is issued, or if it's on the ground. A thunderstorm is a response. Remember, it's a response to the immediate environment. So even if everything that you have seen says, "Oh, there's not going to be any thunderstorms," then you would say, "Oh, something in the data, the models, the observations. You need to go back and see why there's thunderstorms." So if there's a supercell environment, no matter if it's in Florida, Alaska, or Oklahoma, there will be discrete supercells. And there's very little coincidence in weather. And you see this example here, and there's actually 5, but I cut the picture down a little bit. But you see there's 4 supercells. And one thing you notice, there's a boundary to the south. So what happened here was in Supercell 2, which is the one right off the coast, that was an EF3 tornado at Kinglands, Georgia, at the submarine base, which I don't know why we're seeing this picture if it's from the submarine base. It's top secret, he was saying. But what happened on Supercells 3, 4, and 5? Does anybody have a guess? Would you have issued a tornado warning, or would you issue severe thunderstorm warnings, or would you expect hail, damaging winds? Anybody on that?
Maybe back up so we can remember where they are.
Okay,
Are they
sure.
north of a boundary?
Yeah.
Oh,
3,
they are.
4, and
Okay.
5. Yeah. So that's what happened. And so what happened on 3, 4, and 5? Well, they were impacted by northerly cool outflow from supercell number 2. The lower level shear profile was very different. They all had mid-level rotation, but were weak at the surface. And Jacksonville, in this case, issued a tornado warning for cell 2, but severe thunderstorm warning for 3, 4, and 5. And you'll see this in his introduction presentation if you take it. And what they did is he said that actually resulted in the tornado warning not being out for as long, and it was also for a smaller area, which also my cursor here, their tornado warning was more in for this area on 2. And then this had this whole area as a severe thunderstorm warning. And a lot of that was based on their meso analysis that was going on at the time. An example, what you could do is you could, we get these, like we say, the marginal risk from SPC. You can use a local scale and tactical threat assessments and messaging to enhance your DSS. You use our local tools and whatever, and you can provide a little more expertise through social media to tell what's going on. And what they found, if you could read the Mesoscale update from Miami, they were able to say there was going to be some supercells development, discrete supercells forming in the southern Florida panhandle, besides just saying, oh, there's a marginal risk. So if you could kind of think of what you're expecting, the type of storms you're expecting, you could communicate that and maybe what the threats for the day are. Now,
Hey,
yeah.
quick question. Sorry if you said this and I missed it, but on that Jacksonville example with the tornado warnings or tornado warnings, how did those severe warnings verify if they were impacted by that cool outflow?
Well, they actually produced. I'm sorry. They actually I think one produced some hail, and the other ones did have some winds. I guess the cool air wasn't strong enough to keep the winds from getting to the surface, but they didn't produce tornadoes. And
Okay.
and if you didn't know the boundary and all that was where, I would say, oh, well, I'm going to issue 4 tornado warnings. So
Right. Okay. Thanks.
that's the point of that. So they've issued this course. It's in 3 parts. There's an assessment. There's actually a very detailed section of courses, and then there's a lot of examples. And I've taken about 20% of these. They just introduced it a week and a half ago, and I was thoroughly impressed. Now, there's about 40 hours worth of training here, and I don't expect everybody to go through every one of these modules. There's a couple that they suggested that everybody do, but a lot of these I would, if you feel like you're not need a little more work on it, you can take them. And so that's where, some things, if you want to look at the crosswise streamline vorticity and SRH, these trainings are excellent. So an example here, these are all the assessments, and the assessments take about 5 minutes, and all they are is a sets of 3 to 6 questions depending on the subject. And then what they do is they just ask you these questions and you answer them. And if you get them all right, then you probably don't need to take the more detailed module. If you see like 1 or 2, you may want to take the module. The other thing is these are probably the most up-to-date mesoscale training things. They're current, up-to-date to now. So there may be some interesting studies that you could increase your knowledge on. So let's show an example of what this part 1 service science assessment would look like. This is an example for residence time for severe storm longevity. And they will ask a question. You're just clicking, you'll start it, and it will ask this question: which of the following scenarios would yield the longest residence time for thunderstorm within the buoyant sector and the shortest duration? Anybody would like to give a try at that? Everybody's shy. Well, since everybody's just jumping up and down for it, the answers are A and C. And the reason is I was going to say the longest one would be because we've got a buoyant sector motion, and then the storm motion are the same speed, and it will continue with time to move over to the right. The shortest would be because the buoyant area is not moving, but the storm's moving 30, so that would be the shortest. And there's an explanation of how that works. So then we go into the part 2, and these are a lot longer. A lot of them are 30 to 45 minutes. The longer ones, like you see, the advanced QT is 60 minutes. I will tell you now, I took part of that, and I didn't take the whole thing. I ran out of time, and they mentioned to it, it is more of a graduate level, and it's excellent. And I would recommend, if you have looking for some training, to do that one. Some of the other things the 2 that I took, because I'm going to talk about it in a minute, is the CAM fundamentals and the CAM in operations. Those were absolutely spectacular, and they have case studies. They tell you what some strengths are, the limitations are, what to look for, and what is being used, especially in SPC's ensemble CAM. So you can see those, and you can see they also have the tools and techniques, how to do things in operations, and also for communications for IDSS. One example here that I saw was targeting lightning in IDSS. And the example he showed in one of the earlier presentations, that's Peter Wolf, is that, okay, you get an emergency manager. Let's say emergency manager, we talk about the lightning that like at one of the tents for the COVID, and we have the alarm that comes back, and it's supposed to tell us, okay, we got lightning in the area. Well, does that really give them any lead time? It does help to let them know, yeah, there's lightning in the area, but what happens if you could go in and you see there's going to be a boundary, and you says, well, there's possible lightning in 1 to 2 hours, and this will show you some techniques how you may improve that. So that may increase the lead time. Some things may just be based off climatology, like where sea breeze or the differential heating from the sand hills to the coastal plain. But excellent. I don't expect it, like I say, they're there for all of us. I will actually assign a few of these that were recommended by the group that everyone should go through. But this is a great source of information and help you brush up on your skills. The third part is and I didn't put it here, is actually the courses. And there's actually 9 case examples of convection, different types of convection, different types of things. They're very, very detailed and they're great. So you can go through some of these things. You can go run the case examples to practice and see how the techniques work. So I want to give this example in part 2, like cam fundamentals. And this is from Chauncey Schultz from Bismarck, North Dakota. And hang on a second, I got some cheat sheet notes here I wanted to put up. Sorry. If you go in and look at some of the cams and some of the things you find out from it, that many differences in the cams are from model course, assimilation frequencies, internal lateral boundary conditions, and PBL schemes and microphysics schemes. But do you know which models have which and why and their biases? Well, this module actually helps. And here's an example showing that PBL schemes that the HRW uses is the YSU scheme, which is non-local. And what it does, it over-deepens the planetary boundary layer, resulting in too much dry air near the surface. So there's an underestimation in the mean layer CAPE and the mean layer SIN. So you can see all those things. So excellent, excellent points there. There's a high shear low case example they talk about, and how each model, you can see the HRW, ARW, which is in the top left here in Arkansas. And these are paintballs, and the paintballs are showing where the 4-hour, 2 to 5 kilometer upward helicity is, which is a proxy for mesocyclone development. And you can see here where this is where the HREF was trying to forecast those, and the red dots are actually where they had tornadoes. And you can see down the HRW is not the HRW ARW is that's 12 hours, which is a time lagged, was not as good. And the HRR, as you can see, didn't do too well in that. And also you can see there's examples of, you can look at the stamps of all the models, and you can see which one favors and so forth. But the one thing you notice that, well, you can see when what performs poorly in weak forcing to aggressive in SIN or CAPE, we found that the errors that if there's, like, especially in morning convection, if it's showing convection starting up, like in, let's say, out here in Oklahoma, back out here in Oklahoma, and it's not occurring, well, you know that's probably an error, and you're using your high-res satellite, your radar observations, and it's not going. Well, what they found out is those cascades were error, and it will just start producing convection, and it may not occur. Common convective initiation biases in these cams. Generally, we see the NAM-CONUS nest tends to trigger convection too early and aggressively. The NSSL WRF ARW tends to be more conservative with creating convection. And the HRRR, its microphysics scheme, the Thomson microphysics scheme, can be too slow with cold pool propagations when that exists. So a lot of these things you'll learn from these courses. And like I say, I'm just very impressed with Chauncey's modules here. And here's the example again of the case examples of convection. And we do have some close. There's one in Northeast, Southeast Georgia, QLCS, and there's a few in our area. So I just wanted to go over that. And the key is that with this mesoanalysis, their big point is somebody says, oh, we have somebody doing two things. They really want to show the importance of a mesoanalyst during severe weather outbreaks, and it's very important. And this person, the radar person, shouldn't do this. The mesoanalyst will be pointing this stuff out. And also, it's awful hard to do this and also do IDSS. And I wish Mark was here. Mark's out for about an hour because he's in the MIC call. But that's something we need to consider if we do if we have a meso analyst. I believe in what they're showing, and you can help me out. I think it would help us with our IDSS. I think it could help us with some lead times. Not always going to be perfect, but it's definitely a way to improve. Now I want to show. Let me bring this over. The HREF, and I imagine a lot of you use it, but I'm going to right here. This is SPC site under Forecast Tools. There's the HREF. And I don't know if everybody knows this or not, but you can go back in time and look at things in the past. And I'm going to go to the 12Z on the 15th. Now, the HREF is an ensemble of convective models and that produce convection. And this is run. They use I'll show you in a minute what makes them up. But this runs 4 times a day, but the website only shows it at 0 and 12Z, and it comes in at the 12Z is available at 16Z, and the 0Z is available at 4Z. So when we look back at the 15th of May, 15th of February, that we'd only have access to the 12Z. So the operational version here you see on the right is version 2, and what are the HREF members? If we look here on the right, the version 2.1, with the members are the HRR 6 hours time lag back, HRW ARW, a 12-hour version of the ARW, the MMMB, and so forth. You can see the HRW and SSL and NAM's CONUS Nest, and they're you can see the lateral boundary conditions are listed in this column, and and also I believe the convection if it starts up is from here are the rats. Some are time-lapse back, some are not, some are from the NAM. We have microphysics packages, what they are, the different types of planetary boundary layers. Here are the resolutions. You can see the HRR is 3, the vertical levels that were in there, and then how many hours are included in the HREF. So that's available. And if you can't remember, it's just right there on the right side. They also talk about what neighborhood probabilities are, and I'm just going to show you that. It's pretty much are calculated, you see, on a 3 kilometer grid. The neighborhood box is specified by radius. It's about 40 kilometers. The neighborhood is about 80-kilometer box centered on that point. And the grid probabilities for exceeding that threshold within the neighborhood are calculated each point and so forth. So that's how those neighborhood probabilities come out. So when we look at this, so Mark wanted to do kind of a synoptic overview. I have some other graphics, but I'll do that quickly for this, just so we see it when we get for the hot wash. You can see here's the 500 millibar heights the morning before. You can see we have a trough coming through. This is at 500 millibar, so you see a jet that's coming over the Appalachians there in eastern Tennessee, and it's moving on out. 850 heights. These are all means, and this is from the model. Let me see if that update. There we go. And here's like the heights here, and the other field here. This is the winds, and you can see the low-level jet. And if we get down to the time about 4Z to 5Z, you can see the low-level jets coming in. Now, this is 12Z, so this is 16 hours before. If I go to 0 of 16 and look at this, you can see some of the changes. But like I said, this is not available at that time. Some of the other, you can get the heights, surfaces, so forth. But you got severe weather. You can look at the capes here, the mean max capes. You can do that. And here we'll go to 4Z. Let's go back to the 15th to 12Z. So I don't want to we wouldn't have access to that. But you can see we'll go to 4Z here as it loads up. And you can look here. Oh, let me see if I can stop my mouse there. Sorry. Well, we'll go 3Z. If you can notice here on the right in the product overlays, from that, you can display here what the max ensemble max cape is. There's the mean and there's the min. So the worst case, best case, most likely case, and the best case. And then you can actually change here on the right. What I've got is a 10 meter into 500 meter bar shear. That's the barbs, and then ensemble mean in the capes. Then you can go to, you can put up here the shear as contoured versus barbed. You can also put surface-based sin on there, overlay, and the 1 hour max. And you can see if I turn, you can see the brown there at 3Z, and it does show the one coming on custom, but look when it is 6Z. But but when we look at it even more on the members, and I'll talk about the storm attributes here now, for the Mac, you can look at these updraft helicities, and what they're just proxy for mesocyclones. That's all. And generally, when you get 100 greater than 150 on the neighborhood probability, it's a pretty good indicator you get tornadoes. And it's, if I move across here, you can see there really wasn't that much in that. Also, I can change this down to the southeast. But the other thing that I like to do is look at the PB, which is the paintballs. And what it does is it shows every model down here in color where it's actually seeing upward helicity greater than 75 over a 4 hour period. And you can see it starts at 16Z, and then we'll come back to 4Z, and you can see it's one model, like say it was late, but did it show the close? That's HRW time lag 12 hours back. So it kind of just shows you the area. This here does not show much confidence because they're all spread apart. If we get a case where everything is kind of all back together, then you get like this right here. This would probably give you more confidence if this was land that you would have tornadoes. So that's available. This is something that you would prep before the event, and this is also where the mesometeorologist could use this to help put out this information. Other things here we have, you see max wind speed. Here's the paintballs for wind speeds greater than 30 knots with time. Now this gets to be a mess because you have all these, let's go to 4Z, you have all these models here that are showing where it's 30 knots. You have a few over here. But if you want to figure out which one, you can turn each one of these members off to see where which models are producing. The purple is, I believe, is the ARW, and the HRW NSL time lag minus 12 showed this area here over the coast. But I just wanted to show you that is available for you to look at. And the things I noticed in the synoptic, we had the course with trough, and we had a pretty strong jet coming across, and the upper level divergence was extremely strong. So the synoptic scale was pretty good. The question, even in SPCs, was, and we get this so much, is it going to make land or not? And to be honest with you, it was a low probability event that it would come in on shore like that. So that is what I have there. And then finally, if everybody's still awake, which may not, Mark Willis wanted us to come up with a WES just so everybody gets a chance to look at this storm and kind of diagnose it. So I have put together, there's actually two parts of a job sheet. One is just, the first one is the job sheet for reviewing the data is how to actually set the case up if you want to do it on your own. And the first time I will go through with everybody to help set it up, get you logged in. And once how to set it up is the same for everyone. And this just gives all the instructions. Then in the case review, I have a document with just some ideas of what I think you may want to look at. I have set up a few procedures. I took some from the WDTD group from some of their rack courses, and that. So what you have to do is, because the WES is old and it has some issues, but you would tell you how to open up procedure, show all users, click a procedure, this 000 February 16th procedure, and then the first procedure will drop you into pretty much Pender County down to Georgetown. And what I'm trying to do is have you look what it looks like when it's offshore, like Merle's Inlet, all the way up as it goes up to the north to the Columbus, Brunswick County line. And here are some of the procedures. And like I said, these are the first two I have questions based on them. The other ones are just there for your use. You can use your own procedures that are on the WES. Just so you can look through. And so what I do is have you set the AWIPS to 520Z, go through the storm motion and the radar display control, and I'll let you pick out, and I want you to set the SRM for 318 at 42 knots, just so we're all kind of looking at the same SRM packages. There's some cautions in here. The 9-panel display on this older version of AWIPS, it wasn't built to handle 9 panels, so the numbers are wrong, and you can't display the first panel in a big screen. There is one in there, but you can't flip back and forth. And if you have bad eyesight, you may want to zoom, blow it out so it's 1 panels on one screen. So 4 panels in this case are more helpful. Hopefully, when we get to, I'm guessing it's going to be the WES in the cloud, because we can do the 9 panels, which to me are more conducive for your warning operations. Sorry, there's no FSI available for the case, and there's a question there about the CAPI, if that would be how to use that. Satellite data is limited to ECONUS, and we didn't archive it quick enough, and the lightning data wasn't available. So I would like you just to feel free to look at any of the radar data. You're not limited on the time, how much you spend on. And I just ask a bunch of these questions. And like I said, we'll start next Wednesday, and I'm going to have a sign-up sheet for everybody to go through it. And it's going to go through the end of I'd say deadline to get most people through by tax day, April 15th. I'm off for a couple weeks in the middle, but I'll work y'all through this. And then I have all these just kind of some guidelines, what to look out. There's more stuff you can look at. If you have any suggestions, please do talk to others about it. But at the very end, I have points to ponder with the staff. And Vicki made the point about sales. Which sales would you use? We'll talk about that in a minute. Would you use the Merle? Also, what sales cuts would you use if you use sales or Merle? What would you use for something in Lake City? So there's a lot of questions there. That is just for discussion and for you to think about and just kind of place back in your memory when cases come up. And I'll just say, the last thing I'll say, this was you'll find out extremely difficult. The clutter was terrible. Everybody, from us all the way up to the top, all know that the tree blockage really affected, and that's just in-house knowledge for that one, because Steve has all those talking points and stuff like that. And we're just going to try to, until we get something done, hopefully sooner than later, that we have some ideas how we can try to mitigate some of these issues. And I just want to make sure everybody knows those. Some people already have their techniques, and that's fine, but I just want everybody to know and have it. So if this thing comes up unexpected, like a storm, that you'll be ready to handle that. So, Mark, I went way too long, I know. And is there any questions? Is my microphone on?
Yes, you'd sound just fine, Reed. Well, we're going to have a big discussion at the end, so.
Yeah, that's fine. Yeah.
You hear me?
Yes.
Yes.
Is that storm motion 318? I thought it was more towards the northeast.
That is the center of the storm motion of the cell.
The northwest?
That's what I calculated in the storm track. STI showed that value. So that's just kind of a standard to put in. You can actually get 322 or something. Yeah. But 318 was more close to what it was.
Yeah, I thought they were moving to the northeast, not the northwest or northwest.
Okay.